In this video we were going through the first part of Progress Test A, that is the structured questions. The multiple choice section is covered by a separate video. Now question number 1 is about fossil fuels, and the first focus is a petrol fraction from crude oil and specifically octane. You're asked to give a balanced equation for the combustion of octane, and with 8 carbons we would therefore expect to get 8 moles of carbon dioxide. Complete combustion forms carbon dioxide. 9 moles of water because there's 18 hydrogens, and therefore 12.5 oxygens would be needed to balance the equation. In part B, the focus now moves to the pollutant nitrogen monoxide, and you're asked to give an equation of how nitrogen monoxide can be removed in a catalytic converter. The simplest equation to learn would be the one that involves nitrogen oxide reacting with carbon monoxide, and you would expect to form carbon dioxide and nitrogen, and you can see the reaction is 2 moles of nitrogen oxide, 2 moles of carbon dioxide formed, and 1 mole of N2 produced. The focus shifts slightly now to focus on sulfur dioxide. That's, as it says there, produced by the combustion of fossil fuels, and you can see the emphasis is how that acidic gas is removed by using calcium oxide. Now you can see here that you're given a fact: in 1970 the total UK emissions of sulfur dioxide was 6.49 million tonnes, and of course you're asked to calculate the mass in kilograms of calcium oxide that would be needed to react with this acidic gas. There are a few things that can trip you up here, so some things to be aware of would be the numbers that you'll be using. 6.49 million, well that is 6.49 times 10 to the 6 tonnes. But of course when you do your mole calculations you're going to need to work in grams, and actually to convert tonnes to grams you need another factor of 10 to the 6. So when you look at the calculation that I've got written out here, you'll see that I'm going to use 6.49 times 10 to the 6 times 10 to the 6 again. That's bringing in the million and the tonne conversion for grams. In fact, it's simpler to write that simply as 6.49 times 10 to the 12. And there we go, there's the calculation. The number of moles of SO2 are 1.012 times 10 to the 11 moles. Now of course I'm after the number of moles of calcium oxide, and when I look at the balanced equation I can see the ratio of calcium oxide to sulfur dioxide is 1 to 1. Therefore I would need 1.012 times 10 to the 11 moles of calcium oxide, and I can calculate the mass in grams, and you can see my working in there by taking that number of moles and multiplying it by the MR. Of course what I'm expected to do is I'm expected to calculate that mass in kilograms, and so I'm going to need to convert from grams into kilograms, and I've done that by dividing by 1000 or by timesing by 10 to the minus 3. And that is your answer for question 1. In question 2 we kind of switch focus to structure and bonding. The diagram you can see there I've already drawn. The question asks you to look at the strongest type of interaction between 2 molecules of ethanol. That of course is hydrogen bonding, but there's 3 marks up for grabs here, and you have to be aware of the criteria that are expected. If you have a quick look at the question, of course it does prompt you to do this. You are expected to include all lone pairs, and now I've done that. The oxygen atom has of course 2 lone pairs, and I've put the 2 loads on each oxygen. If your diagram does not have 4 lone pairs, you are going to lose a mark. You are also asked to bring in the partial charges. The partial charge is delta plus on the hydrogen, delta minus on the oxygen, but that should be present in both molecules, and in fact the first mark is for including those bits that I've highlighted then in yellow and blue. Now you can see that I've shown my hydrogen bond from the lone pair to a delta plus hydrogen atom, and that's needed to get the second mark. The hydrogen bond should be the attraction between a delta plus hydrogen and a lone pair. But actually the exam board are very fussy with how you draw that, and they would expect that there's a linear relationship, and you can see it being highlighted in green here, a linear relationship between these 3 atoms. The oxygen with the lone pair, the hydrogen bond itself, the hydrogen of the OH group that's bonded to the lone pair, and that oxygen, and you can see that green line, that should be present for 3 marks. So your first mark, 4 lone pairs, and 4 partial charges. Your second mark, the hydrogen bond drawn between the correct hydrogen atom of one ethanol and a lone pair on the oxygen of another. And your final mark of the 3 is that linear, nice, neat diagram. The second question moves on to methoxy methane, a chemical that you've not necessarily come across, and it doesn't matter because you're given some data that you can interpret. You can see here you've got the boiling points of both ethanol and methoxy methane, and you're asked quite a classic question to, in terms of intermolecular forces, explain the difference in boiling points. Before we do that, I'm just going to show you very quickly why I've drawn this molecule out. Methoxy methane, with the oxygen in the centre, 2 lone pairs, 2 bond pairs, would be V-shaped around that oxygen, but the key thing to recognise, of course, is oxygen is electronegative, and therefore these 2 carbon atoms would be slightly positive, the oxygen slightly negative. This molecule is a polar molecule and would therefore have a permanent dipole. Now that helps me in this question because I might not recognise the molecule itself, but by drawing it out and having a think, I can see that the intermolecular forces I would expect would be permanent dipole-dipole interactions. And my first mark is for that, recognising the intermolecular forces between methoxy methane, and you can see here permanent dipole-dipole interactions between molecules. Now there is an extra circumstance you can bring in here, because this is an unfamiliar molecule and it was taken from an AS exam paper where the mark schemes have a greater degree of leniency. You were allowed a mark if you said there were van der Waals forces between molecules. So if you're looking at your work and you realise you got a mark for saying van der Waals, well, that's because in this case the mark scheme was generous and it did allow that, although I would encourage you perhaps to think about putting the correct intermolecular force in rather than just hoping in future instances that you can get away with van der Waals. It was an AS question, not an A-level one, and obviously in your exams in the summer you expect the mark schemes to have a higher degree of accuracy. Now ethanol, of course, we've just drawn it, so we needed to recognise there are hydrogen bonds between the molecules, and I'm on to my first 2 marks. One for the intermolecular force in methoxy methane, one for the intermolecular force in ethanol, and my final mark, my final sentence here, is that hydrogen bonds are stronger than permanent dipole-dipole interactions, and so require more energy to break. And just raise it up there on your video screen, and here it is. Hydrogen bonds stronger than permanent dipole-dipole interactions, more energy required to break them. And you can see I'm referring to the intermolecular forces. The question does want me to do that. I'm not using horrible phrases like breaking bonds or anything like that, because in A-level exams that would often result in a chemical error and in 0 marks being awarded. Now part C moves on to shape away from bonding and structure, and actually you're introduced to yet another unfamiliar molecule at which you're expected to work with, and there's perhaps a more familiar example. Let's look at the focus of the question first of all, then we can get into looking at the answer. So you're asked to draw the shape of POCl3 and the shape of the ion ClF4, including any lone pairs that would influence the shape there on the central atom. You're asked a little bit more. You're asked to name each of the shapes, and for the ClF4- ion, you're asked to suggest a value for the bond angle. And of course, highlighting the question, you can see you're given some information in the middle there. That information, of course, is going to be helpful, because in POCl3, a molecule that you might not have come across, in fact probably haven't, you can see that the oxygen atom is attached to the phosphorus using a double bond. Now if I begin to draw this out as a bit of working, that sentence tells me I've got a double bond between the phosphorus and the oxygen. Now that uses 2 electrons from phosphorus. Phosphorus is in group 5. 2 of the 5 electrons are already involved in bonds. That leaves obviously the 3 remaining electrons to bond to the chlorine atoms. So POCl3 has this sort of structure. Now I'm looking around the central phosphorus. All 5 electrons in the outer shell are now involved in bonding, but really there are only 4 areas of bonding: the double bond and the 3 bonds to the chlorine atoms. So with 4 bonding areas, I would expect my shape to be tetrahedral. And of course I'm going to make my life easy by keeping that double bond in the plane of the paper. I'm going to have one of the chlorines in the plane of the paper as well, and I'll expect a chlorine coming towards me and a dashed line to represent the chlorine going behind, and I've picked up a mark for my first shape. Some of you will feel perhaps a little hard done by when you look at your work because you've drawn that shape, but you've maybe not picked up on the advice in the question. There should be a double bond in your diagram between phosphorus and oxygen, and if you've only got a single bond, unfortunately it wasn't allowed a mark. Now with the ClF4- ion, we're on to a bit more familiar territory, and you may have been taught a little formula to help you determine shapes. We'll review that now as a piece of working and as a helpful tool. The central atom is chlorine, and that's in group 7. And there's 4 atoms that are bonded to it, so I'm going to add 4, and it's a negative ion, so I'm going to subtract that charge of -1. Now the formula I've learned tells me that I need to divide that number by 2, so 7 plus 4 minus -1 is of course going to come out to be 12. If I divide it by 2, I've got 6 electron pairs. Now those 6 electron pairs around the chlorine are going to contribute to its shape. 4 of those pairs are involved in bonds because there are 4 fluorine atoms, so I'm looking at a shape that has 4 bonding pairs and 2 lone pairs. So I'm going to draw my chlorine in, I'm going to show the 2 lone pairs, I'm going to put them above and below the chlorine, and I'm going to have one of the fluorines coming towards me, one on the other going away, and the same on the opposite side, so a fluorine coming towards the plane of the board, coming out of it I should say, and going in. And that shape of course there is going to be square planar. And that one is perhaps a more standard example that you will have covered similar examples with the notes last year. Now we've already hinted that the shape of the POCl3 is tetrahedral, the ClF4- ion is square planar, and of course the bond angle in that square planar shape would be 90 degrees. Do make sure when you draw the shape diagrams that you do follow the advice in the questions. Again, we reiterate with these examples that you might not have seen before, you will be given advice, for instance, about the double bond. You will always be expected to show lone pairs on the central atom, so do make sure your diagram includes those lone pairs. Now question 3 starts looking at mass spectrometry again from the point of view of an AS style topic, and the first thing we're shown is we're shown a mass spectrum. What we are told of course is that mass spectrum is achieved by electrospray ionisation, and one of the things that I will bear in mind for a little bit later in this question is that when I see that peak it represents an ion that is formed from my compound and H+. And that's where electrospray ionisation comes in, and the first part expects me to recall how this type of ionisation takes place. So of course if I go to atomic structure, the first topic we did part 1, you will see this written down. What we need to do is dissolve our compound P in a polar solvent. Let me highlight the marks as we go through them. So P is dissolved in a polar solvent, and it's injected through a needle, but that's not quite enough detail. You need to say that it's injected through a needle and that needle is attached to a high voltage supply. So again, you can see a green highlight there covering the key points that you would need to include as part of your description for the second mark. The final mark of course is that particles of P are going to gain a proton or they're going to gain H+, and that's how they form a positive ion. That H+ would come from the solvent, but the mark scheme really is about key detail, and it's the gaining the H+ that is the bit that you really need to include. You're asked to give an equation to represent that ionisation, and in fact if you know the methodology of course you can see it there in the middle of the screen. I take my compound P, whatever it is, I'm going to add H+, and I get my new ion, there it is, my pH+ ion. And it's that ion that is detected by the mass spectrometer. So when I go to the next page and I'm asked what the relative molecular mass of P is, I need to make sure I fully understand the context of this technique. It's this ion in the mass spectrum that is detected. So the peak is for this ion, and the peak occurs at 556. Many of you who sat this exam will have been tempted then to put a tick in the 566 box. You can see I haven't. My tick there is in 555, because if you think about the mass of this, the proton has a mass of 1, and therefore my mass of P, which is what I'm interested in, must be 555, and when I put these two things together, the total mass of my molecular ion would be 556. And then perhaps unsurprisingly, because it happens quite a lot on your A-level exams, certainly on paper 1, we would expect a question that involves time of flight mass spectrometry calculations. We'll just scroll down and have a look at the question before we talk through the steps. So a molecule Q here, a different molecule now, is ionised by electron impact ionisation. Q plus ion has a kinetic energy of 2.09 times 10 to the minus 15 joules. So there's a number we're going to need. We're given a kinetic energy. We're told that the ion takes 1.23 times 10 to the minus 5 seconds to reach the detector. Of course, that recognition then is I'm given a value for the time it takes for that ion to travel through the flight tube. And I'm told the length of the flight tube is 1.5 metres. This, of course, is going to be the distance that the ion has travelled. And if we just label that up there, that will help us when we get a bit further in this question. So what am I asked to do? Well, here it is. I'm asked to calculate the relative molecular mass of Q. I'm given the kinetic energy equation, half mv squared, and I'm given the Avogadro constant as perhaps a little bit of a prompter that I might need it. Well, I've got to calculate mass, so the first thing that I would do is I would rearrange that KE equation. I'm going to double both sides to get rid of the half, divide through by v squared, so the mass in kilograms is 2 lots of the kinetic energy divided by v squared. If I'm able to rearrange that equation, I pick up my first mark. Now, looking at the numbers I'm given, I am given the kinetic energy, but I'm not given the velocity, the speed, in detail. So my next step really will be to calculate that. I am given the distance and the time, and I can calculate the speed here, and you can see that I've got a value of 121,951 meters per second, and you can see my working as well. Well, that means that now I've got my value for velocity, I can pop it back into my equation, and you can see the numbers that I'm using here. I've got the kinetic energy straight from the equation, I'm doubling it as in my rearranged form, and I've put my new calculation in there, also my new number for velocity. Just watch out for this one, because if your mass doesn't come out to be the same as the one that you're about to see on the screen, it could well be that although you meant to, you didn't, and you have omitted that square term. You might have written it down, but you might not have included it in your calculator. So the mass in kilograms of one of these ions, Q then, is 2.81 times 10 to the minus 25. So we're on 3 marks out of 5. I've got the mass of one ion in kilograms, and I need to convert that into the molecular mass. Well, actually, the molecular mass is linked to a mass in grams, so I think it would be logical here to turn that mass from kilograms into grams. So I'm going to times it by 1,000 to come up with 2.81 times 10 to the minus 22. So there's a mass in grams. That's the mass of one ion, or sorry, one molecule I should say. And I want my mass of 1 mole, my MR, and that would be 6.022 times 10 to the 23 lots of this mass, because that is the number of ions or molecules you would have in 1 mole. So you can see in my final step there, that is what I'm doing. I'm taking my mass in grams, timesing it by Avogadro's number, and the answer here, 169.3 for my relative molecular mass. Now these last 2 steps, of course, you can do in which order you see fit. Some people like to go from the mass in kilograms, work out the mass of 1 mole, and then scale it back down into grams. It's up to you. The key thing is, if you get the right answer, your method is sound. Question 4 moves on to equilibrium, and it's an equilibrium involving nitrogen, oxide, chlorine, and NOCl. Again, some of the compounds we might not have come across, but it's not going to worry us with our questions. So 1.5 moles of NO are mixed with 1 mole of chlorine, and the mixture is left to reach equilibrium. Now, of course, what I want you to recognise here is that we're dealing with a start of a reaction. A reaction is started, and what I'm doing here, and I'm going to use the word initial, is initially I am adding this number of moles of 2 of the chemicals in my equilibrium to my mixture. Then I leave it. And of course, when I get to equilibrium, and you can see it here, the equilibrium mixture contains 0.35 moles of NaCl. So now I've got a kind of an after that initial scenario. Now I'm at equilibrium, I've got 2 conditions. This is going to be one of those classic Rice questions. So I've begun to set up a table that you would have seen in the notes, and you can see I've begun to take the information out here from the question. So initially I've got 1.5 moles of NO, 1 mole of Cl and none of that NaCl in the mixture. Now, in my equilibrium mixture, I have got 0.35 moles of NaCl, and therefore I've now got my change. And that's obviously what the C would stand for, the change. So we can see that the number of moles of NaCl is going up by 0.350. We can use that now as our reference point. That we can then compare to the other compounds. Now the other compounds are on the other side of the equilibrium, so if I'm making NaCl, I'm obviously using up NO. How much NO am I using? Well, if I look at the ratio between NaCl, so the balancing number is 2, and the balancing number for NO is 2, then they're in the same ratio. So if I'm going to make 0.35 moles of NaCl, I'm going to expect 0.35 moles of my nitrogen oxide to have reacted. So to work out the equilibrium moles, I would do 1.5 minus 0.35. Now, of course, for chlorine, that is also going to go down, and it will go down by a factor of 0.35 moles, but the balancing numbers here are different. You can see here the ratio changes. For every 2 moles of NaCl I make, I'm only going to use 1 mole of chlorine. So that change, I'm going to divide by 2, and so to work out my equilibrium moles of Cl2, I'm going to do 1, and I'm going to subtract 0.35 over 2, and the final answer, as you can see on the screen for you, would come out to be 1.15 and 0.825 for Cl2. The next part should be relatively straightforward. I'm asked to give an expression for my Kc, and of course if I go back to the equilibrium, there we go, we're going to have our reactants and our products. It's the products that would appear on top, the reactants underneath, and I'm going to take into account the balancing numbers. So on the top line, the concentration of NaCl squared, its balancing number is 2, and on the bottom line, NO squared, again its balancing number is 2, and I'm going to multiply that by Cl2, so multiplying the bottom 2 numbers together. For the final part of this question, I'm expected to do a calculation, and to make my life easier, it's not consequential on anything I've done before, so if I haven't been able to work out the right calculations, I'm starting afresh here with some new numbers. Now a different equilibrium mixture is prepared, and the flask there has a volume at 800 centimetres cubed at a different temperature. I've underlined it, but we'll put a highlight on it so you can see it on your screen. At equilibrium, the mixture contains a certain number of moles of NO, there it is, 0.850, and a certain number of moles of Cl2. So recognise there, in terms of the data you're given, you are given a number of moles. Now, you're also given some data about Kc. This time I put it in a little red box. So I've got a value for Kc, and the question is just below. Determine the amount in moles of NaCl in this equilibrium mixture. So, this was the Kc expression we had in the previous part, and what I'm going to need to do is rearrange it so that I can calculate NaCl. Now what I'm going to do, of course, then is take this expression, this part at the bottom, I want to move it to the other side by multiplying both sides by it, and that would give me an expression that looks like this. NaCl squared is Kc times NO times Cl2. But of course that's not finished, that's not going to help me calculate my number of moles of NaCl, because that is currently squared, and so to complete the rearrangement, my concentration of NaCl would be the square root of Kc times the concentration of NO squared times the concentration of Cl2. Now at this moment I've picked up my first mark, I'm demonstrating to an examiner that I know the methodology on how to solve this problem. And now I can put about some numbers and start calculating that concentration. There's something to be aware of here, and when you look at my work, and I've left it all relatively big, I've not separated out the values here. I've got my value of Kc, so there's the Kc, 1.32 times 10 to the minus 2, and now I need to include my concentration of NO squared. And of course you can see I've gone back to the question, and let's just scroll up and have a look at that question. There's the number, 0.85 moles of NO. But recognise, we circled it, talked about it earlier, that is a number of moles. I need to calculate the concentration. I'm given the volume, and you can see it's there highlighted in yellow, So in this calculation, my concentration of NO would be the number of moles, 0.850, divided by the volume in decimeters cubed, 800 times 10 to the minus 3. And I've got to do the same for chlorine. You can see I've got the number of moles divided by the volume. So this second mark that we've got here is for using the volume of the reaction mixture to correctly calculate the concentrations of both NO and Cl. A lot of people, when I looked at this, didn't do that. They tried working with the number of moles. You do need to work with concentration if you're given a volume. Now, if I do all that correctly, what I should get then as my concentration of NaCl is 0.0924 moles per decimeter cubed, and being able to rearrange the equation, calculate the quantities I need in terms of concentrations, and then express it all correctly and perform that calculation, I would get my third mark. And obviously it's tempting at this point to stop and think the question is done. We've rearranged Kc, we've put in the numbers, we've spotted that we need to work out in concentration, so we've used the volume, we've done and used all the data in the question. But go back to the question and have another look at what you're asked. You're asked to determine the amount in moles of NaCl in this equilibrium mixture. So yes, we've worked out a concentration, but that is not the answer to the question just yet. The number of moles, of course, is given by that concentration times the volume, and there it is. If I do that, if I put in my 800 times 10 to the minus 3, converting it per decimeters cubed, I would get a final answer of 0.0739 as the number of moles of NaCl in this reaction mixture. Question 5 then concerns some carboxylic acids, and it starts off with propane dioic acid, and indeed we're going to do a little bit of practical work with this. But before we do, we're asked to draw the skeletal formula. Do watch out for that. When I marked some of these, I did see a fair few that were drawn with non-skeletal formula, so it was clear that you knew what propane dioic acid was, but I couldn't give you the mark because you didn't do it in a skeletal formula way. Now, of course, propane would be 3 carbons, so you can see if I highlight them there, there's carbon number 1 if you like. There's also the carbon at the end of the chain, the 2 carboxylic acid groups bookending this molecule. So carbon number 3 sits in the middle, so propane dioic acid. And again, one of the things we need to be aware of is just how orderly our bonds are. Examiners are very keen that you connect atoms together correctly. So you can see I highlighted in green there the carbon of that double bond oxygen bonded to the oxygen of the OH group. I've got the same on the opposite side. I do need to watch out for that, because if you drew a lovely skeletal formula but you didn't have those groups connected properly, well, you'd have lost the mark. And so it's something to be aware of. Be accurate with your drawing. So here's the practical work then. We're going to prepare a solution of this propane dioic acid. Just focus on the words in the question for us. Describe how to prepare 250 centimeters cubed of an aqueous standard solution of propane dioic acid containing an accurately measured mass of the acid. Include essential practical details in your answer. Well, some of you will like to highlight and underline key things in a question, and I'll show you what's important here, because we are preparing 250 centimetres cubed of a solution. But we're given a quantity here, and we've got to say how we're going to make that quantity. There's something to watch out for a bit later on with regard to that. Now, again, something that might jog your memory here, we're making a standard solution, so that's the methodology you should be aware of. But the last thing to bear in mind is that we need to consider that we've measured the mass accurately in that solution. Now, of course, if you go to your notes from last year and have a look at your amounts of substance part 2, you'll see the method for preparing a standard solution, and my model answer is generally based on that method. That would be the one that we're going to use. A couple of things to be aware of as we go through it though. So the first mark, and it's quite a lengthy process to get the first mark, would be to describe how we're going to get this accurately measured mass. The best suggestion we have is that you would record the mass of a weighing boat and a solid. You'd tip the solid then into a beaker and record the mass of the empty weighing boat. The difference between those two masses would be the mass of the solid that's ended up in the beaker, and that's what we refer to as weighing by difference. But you can see with my answer there that I'm giving quite a lot of detail about how that is. I'm not just simply saying I would weigh it by difference, I'm describing what the method is. Recording the mass of the solid in the weighing boat, emptying the solid into a beaker, recording the mass of the weighing boat when it's emptied, and then determining the difference between the two masses. Now at this moment, of course, I've got solid sitting in a beaker. I need to turn it into a standard solution. So the thing that I'm going to be aware of is I need to dissolve it in some water. I'm going to use deionized water. And this point, if you look at official mark schemes, really wanted the word dissolve. But actually, one of the things that you need to be aware of in A-level chemistry is you're supposed to pick suitable equipment. So you can't simply say you're going to dissolve the solid. You need to give some indication of what you're dissolving the solid in. So I'm saying that the solid is in a beaker. I actually mentioned the beaker earlier. That would be enough detail. It's clear that the solid is now in a beaker, but I want to draw your attention to the detail that you would need to give. Some of you added the detail about stirring, and that would be a good thing to add. I simply haven't put it on here because it wasn't on the mark scheme. I think as a good answer I would say dissolve the solid and stir if necessary to ensure it's all dissolved would be a good thing to include. Now, of course, this is just a solution in a beaker. It's not in any way, shape or form an accurate standard solution. For that, I need another piece of glassware. Now, you can see here, and it all gets a little bit tight on the words, but I'm going to transfer the solution into a volumetric flask. That's the piece of equipment that you need to use, but let me highlight this bit here in yellow. The question said, how am I going to make 250 centimetres cubed of this solution? So I think I should give the detail here that I'm going to use a 250 centimetre cubed volumetric flask. The mark scheme did insist on this, but it is a detail I think that would be easy to miss. So you may not have included it and got a mark, in which case you're lucky. I think it should be there and something to consider. The other thing, of course, is that we've got this sentence, or the end of the sentence is that we're going to include our washings. So you transfer the solution, you'd rinse out your beaker with a little bit of water, put that into the volumetric flask. And at this moment, I've not finished my solution. I need to fill it up to the graduated line, stopper the flask and invert it. Some of you would have picked up on the hint in the question that you need to make 250 centimetres cubed of solution, and you may have said that you're going to take the solid and dissolve it in 250 centimetres cubed of water. And if you did that, you may be wondering why your answer has been marked wrong. Well, because actually in real life you would need a little bit less than 250 centimetres cubed of water. Part of that solution, obviously the 250 centimetres cubed, is the combined volume of the water and the solid will contribute a little bit to that volume. So if you added simply 250 centimetres cubed of water, you would end up with a solution that was slightly more in terms of volume than 250, and it is therefore marked wrong. The graduated line on your volumetric flask would tell you when the solution, the finished solution, had got to 250, so focus your answer on saying I'm using a 250 centimetre cubed flask, volumetric flask of course, and I'm going to make it up to the line, because at that point you would be sure that the total volume is exactly 250. To finish this question, there's a little calculation to do. I've got to calculate the mass of the propane dioic acid that I would need to prepare a standard solution should the concentration be 0.005 moles per decimetre cubed. Now, of course, it's a relatively straightforward calculation. I want to work out my number of moles of acid. That would be the concentration times the volume. Again, I need to be aware here of the unit conversions. Obviously, I want to work in decimetres cubed, but the volume I'm given is in centimetres cubed. Now, watch out for that. I saw quite a few people missing conversion factors. You may be one of those if you're looking at your work. So the volume I'm using is 250 times 10 to the minus 3. That's my conversion to decimetres cubed. That would give me a number of moles of 0.00125. And of course, that number of moles is the number of moles of acid I need. The examiners have been nice to me here. They've given me the MR so I can work out the mass, and there it is. The mass of the acid is my number of moles multiplied by the MR. And just looking at this here, I've missed out a 0. There it is, 0.00125 times 104.0. That would give me a mass of 0.130 grams, and you may have been tempted to stop there. Didn't draw attention to it earlier, we'll go back and have a look now. This question wants me to include a unit conversion. I need to give that mass in milligrams. I'm currently given it in grams, so when I convert it, and the conversion factor would be to times it by 1,000, I've got 130 milligrams. And you're going to see this a lot in the calculations you may have to perform in exams. In order to include the mathematical content, the degree that is needed by the regulators, unit conversions will be present in a lot of calculations. The focus shifts now to a little bit of organic chemistry, and organic chemistry that was covered during that lockdown period. Aqueous sodium borohydride reduces aldehydes but does not reduce alkenes. Show the first step of the mechanism of the reaction between sodium borohydride and 2-methylbutanal. You should include 2 curly arrows. So you're given the question here, you're told what to do, and there's 2 marks. It's not the full mechanism. Again, you're prompted with the answer space here that you want to give the first step in that mechanism. So why are we going to get, or how are we going to get the marks? Well, actually, when I reveal what I've done so far, this isn't yet the complete answer. The reason being, the first mark is for the structure. Can I draw the aldehyde 2-methylbutanal? I'm looking at the wrong question now. I'm looking at the butene. So can I draw this aldehyde 2-methylbutanal? Well, I should be able to. Butanal, of course, is 4 carbons as an aldehyde, but what I'm expected to remember is that carbon number 1 there, in fact we'll label it underneath, it'll be a bit clearer a bit later on. Carbon number 1 is the aldehyde carbon, so carbon number 2 is here, and then I've got carbon number 3, and finally carbon number 4. So I need to include this methyl group in the correct position, so you may have drawn what you thought was the correct aldehyde, but if the methyl group is not there on carbon number 2, you're not going to get the first mark. I've got my 2 curly arrows to do, and to help me with mechanisms I would always generally put some partial charges. The carbon double bond oxygen is a polar bond. Oxygen is more electronegative than carbon, and it makes the carbon slightly positive. That actually helps because now I've got my H- ion here, and you can see that actually sodium borohydride was the reagent. As soon as you see that in exams, you need to be thinking in terms of mechanisms of the hydride ion. That is the bit that reacts with the organic. That is the bit that ends up being shown in the mechanism. Now that's a nucleophile, and a nucleophile is an electron pair donor, and you can see I'm doing it again here that I've labelled my electrons there as 2 crosses. You can use 2 dots, and you can obviously show the H- ion as 2 dots. I would probably go for crosses, the reason being your exam papers come summer will be marked online, they'll be scanned, and if you do dots and you tend to put small dots, little dots like that with a pen, maybe the scanner wouldn't pick them up. If you do a cross, it will definitely be large enough to be seen, and that would be my recommendation. Dots are fine, as long as they've got dots like I've got here that are clearly visible when something is scanned. So I'm going to draw my curly arrows then. So with the blue pen, I'm going to go from my lone pair to the slightly positive carbon. Should be an accurate arrow. You can see there I've drawn it at the centre of the lone pair, right between the 2 electrons. It's touching the lone pair, it's touching the carbon, and I need to include my second arrow. That shows how the double bond breaks, and again, an arrow from the middle of the bonds to the oxygen atom, and that would be my second mark. So I've got 1 mark for drawing the correct aldehyde, and I've got my second mark for both of those arrows being correct, including the lone pair, of course, being involved. Now I need to come on to the written part, and that written part is explaining why the sodium borohydride reduces the aldehyde but would not reduce an alkene. I think the first part would be relatively easy to answer. The mechanism's drawn for you as a bit of a prompt. That's the logic to the question. And so here's the answer. The sodium borohydride can reduce the aldehydes. The key point here, the H- ion is attracted to the slightly positive carbon of that carbon double bond O group. In fact, I'm just talking about the first curly arrow. This first curly arrow in blue happens because the lone pair is attracted to that slightly positive carbon. I've drawn it as a curly arrow. I'm now writing it in a sentence. Why wouldn't it react with the alkene then? Well, that's this structure up here, 2-methylbutanene. Well, the key part to an alkene, of course, is that you've got a double bond, and the functional group for the alkene. Now, there's a couple of different ways you can explain this, but I'm going to keep my argument in a similar vein to this first part. So sodium borohydride won't react with the alkene. Well, when I look at that functional group, and we'll build up the answer here, you can see that that functional group, carbon to double bond carbon, is an area of high electron density. And I've mentioned in that because that's something you're expected to appreciate from your alkene pack. So that is an area of high electron density. What knock-on would that have? Well, you can see here that high electron density would repel the H- ion. If you think back to your reactions that you looked at AS, I'm just going to insert a page for you here. The way you would normally draw a mechanism for the alkene is you would have something like, say, HBr. And the HBr slightly positive on the hydrogen, slightly negative on the bromine, and you'd be used to drawing a curly arrow from that area of high electron density, from the double bond to that slightly positive atom. That's the key difference here. Alkenes as a high electron rich area would react with something that's slightly positive. If we go back to the question that we're looking at, well, we're dealing with H-. H- is a negative ion, it wouldn't interact. So you might have talked about that high area of electron density only reacting with electrophiles. That would be an alternative to the second point. So what I've underlined in blue here, the idea that the double bond would repel the H- ion, you might have said instead that the double bond would only react with an electrophile and not a nucleophile like H- is in this case. Now for part B, where you can see here a student's attempted to reduce this sample, but they've not added enough sodium borohydride. So we can confirm that the reduction was incomplete by using a chemical test, and of course by confirming it's incomplete, you can see a little note to myself I've written there. That tells me that the aldehyde is still present, it hasn't all reacted. So I need to come up with a chemical test for the aldehyde. The one I've come up with here is to use Tollens reagents. That would of course give me a silver mirror. You could have picked failing solution, and in which case if you picked failing solution, your observation would be a brick red precipitate. That would get you the 2 marks. The first for an appropriate reagent, Tollens or failings, and your observation to match your reagent, so silver mirror for Tollens, brick red precipitate for failings. When I marked this for the students in my classes that sat here, I saw quite a few people write acidified dichromate. You were picking perhaps on the fact that we were doing testing for that aldehyde group, and the aldehydes can be oxidized. But just think for a moment about why that isn't allowed. 2-methyl-butanal is an aldehyde. I would expect to reduce that aldehyde to a primary alcohol. So if I use acidified potassium dichromate, acidified potassium dichromate would react with my primary alcohol, it would oxidize it, but it would also oxidize my aldehyde, and really it wouldn't tell me anything. Both of those chemicals, the reaction product and the aldehyde, would turn dichromate from orange to green. So if you put that as an answer and wondered why it was incorrect, well, because your chemical you've picked reacts with both. For a chemical test, we need a reagent that reacts with only one of the chemicals that we're trying to identify. And if it's an aldehyde, Tollens or failings would be the way forward. Now question 7, a focus on esters, definitely moving into this organic field. Now you can see I've got the name already visible for you, the IUPAC name for ester A. Well, when you name esters, you have to focus on the alcohol portion first, and we're going to see a bit of reference to that. And so that's this bit in yellow. And the bit after the second oxygen, the oxygen that's not involved in a double bond, has come from an alcohol, and in this case that alcohol would have been ethanol, and you can see highlighted I've got there ethyl because I've got a 2-carbon branch. Now when I look at the rest of the structure, I've definitely got, and if I highlight them here, I've got 3 carbons. So you can see here that I've got prop and in fact propan because I've got single bonds between those carbons, and the carboxylic acid portion of an ester would normally be called propanoate. So I've definitely got an ethyl propanoate. What makes this question perhaps a little bit nasty is I've got a bromine in here. In fact, that makes it really nasty when we get towards the bottom of the page. But that bromine, of course, is on that propanoate. But the most important carbon in the propanoate is the carbon with a double bond oxygen. That's where the ester would start from the carboxylic acid point of view. So you can see as I number my carbons, and there's nothing wrong with doing this. In an exam, if you label the structure, number your carbons, you can see there that the bromine is bonded to carbon number 3. So 3-bromo for the last part of the name there. So in order, we've got ethyl, 3-bromo, propanoate for our ester A in this case. Now we've got a little diagram to fill in, and we're going to draw the organic products, and do focus on this. We're looking just at organic products for the reactions of the functional groups in ester A shown below. Again, just look at the question here. We are looking at the reactions of the functional groups, okay, in ester A. That's a plural word, and we'll see that in a moment. Now, each reaction forms 2 organic products, and I'm prompted because I've got 2 boxes to fill in, and that allows me to kind of think about where I'm going to write my answers. Now, ester A is drawn for me, and this first reaction is the reaction with an acid. And esters don't do many reactions, and if you've since been back and looked at your notes, you'll realise that esters do one reaction really. That's hydrolysis. And in hydrolysis, the key thing to focus on is the bond that breaks. And I'm going to label it here with a squiggly line. When I hydrolyse an ester, that bond after the double bonded oxygen, the bond between, well, from the carbon to the single bond oxygen, that bond breaks. So what I'm going to draw then are the products that are formed. Well, we said this was the alcohol portion. And with the alcohol portion, then this bit stays exactly the same. And I'm going to use skeletal formula here. It's what I'm giving in the question. I'm not going to change it around. I'm going to present it the way the examiner has presented it to me. That's the group that's fallen off the ester, but it must have come from an alcohol. And of course, it's going to be ethanol. Now on the other side, of course, the other group would be a carboxylic acid. And there it is. So there's my carboxylic acid. And it would be 3-bromo propanoic acid. I'm not asked for a name. I'm just simply asked to draw this section. There it is in red there. That would be formed when that ester bond is hydrolyzed. Now when I scroll down, I get my second reagent. My second reagent is OH-. I'm spotting something here. OH- is the opposite to H+, but I'm going to pause a moment more because there's this extra word. The word excess has been given to me. That wasn't used with H+, so why am I using the word excess? Well, we'll see that in a moment. So first things first, I'm doing hydrolysis, and if you've looked in your ester notes, you can do alkaline hydrolysis, or of course you can do acidic. The arrow that goes up the page is acid hydrolysis. This is going to be base hydrolysis. So if I hydrolyse an ester, yes, I would expect to get the alcohol, and I've got that drawn in already. It's the same ester, it's the same alcohol, so this portion in blue here would be the same. The difference comes now with the other product. The other product, of course, should be a carboxylic acid. But a carboxylic acid is acidic, and acids react with bases to form salts. So under alkaline conditions, I'm expected to recognise that I would form the carboxylate ion. I'm only given OH-, I'm not told if it's sodium, potassium or any other hydroxides. I'm not going to try and show a metal here. There isn't the information to do that, but I'm going to ensure that for my first mark in this section, we'll tell you where the other marks are in a moment, but in this box my first mark comes from that negative oxygen. Now let's drop back to that question again, because there was one thing, and it's very, very subtle, but we put a little circle around it. I'm looking at the reactions of the functional groups. So far I've been focused on esters, because I'm told it's ester A. But there's a functional group here that I need to think about. There it is, a bromine bonded to a carbon. This, of course, is a halogenoalkane. So you should, when you're thinking about this question, bear in mind your knowledge of halogenoalkanes. Do halogenoalkanes react with aqueous hydroxides? Of course they do. Is that why the question here tells me that I'm using excess aqueous hydroxide? I think so. It's trying to give me the clue that I need lots of hydroxide, and that the hydroxide would react with anything in ester A that would react with hydroxide. And so the reaction that I would get here, I'm going to switch to the red pen, is that is a hydrolysis reaction again, but the OH would replace the bromine. We get nucleophilic substitution happening, And actually I'm going to get 2 marks for this structure in this bottom left hand box, as I've put it, because I'm recognising 2 different reactions. The reaction to form the salts, the reaction to form the alcohol at the other end of the carboxylic acid. To show you the other marks, then there were 5 for this part. 1 mark for recognising ethanol is produced in the bottom reaction, 1 mark for ethanol being produced in the top reaction, and 1 mark for the carboxylic acid drawn at the top. 5 marks because I've had to spot 5 things. Now the last part of this question simply says what type of reactions are shown. I've used the word hydrolysis a fair few times now, and you obviously realise that is the reaction that we need. Hydrolysis of the ester, and in this very final box, hydrolysis of the halogenoalkane. Now question 8 would be the last question in this section, and it is perhaps the most awkward. Certainly got one of the hardest questions from a paper 2 that we've seen in recent years. But it starts off with a focus. It's about esters, and it is also about biodiesel. An ester is formed by the reaction of an acid anhydride with ethanol. Complete the equation and with your answer, clearly show the ester and give the IUPAC name of the ester. Now I've got all my answers there for you to see because I want to talk you through really how this reaction works, and so you can piece together the reactants and the products. So the acid anhydride comes up in carboxylic acids and their derivatives. It's part 2 of the notes. Acid anhydrides are used as acylating reagents, and so there is the acyl group, a carbon double bond oxygen and a chain that's after it. Now when I highlight in my product where that acyl group ends up, you can see I've drawn it there. So part of that acid anhydride ends up in the ester. The other part of the ester has come from the alcohol, the ethanol. Now I'll do this as neatly as I can with the board pens. There we go. The alcohol CH3, CH2 and the oxygen end up in my ester, and of course the ester, it says there I need to show it clearly. I can see all the bonds, C double bond O shown out, 2 bonds either side, and then I've put a structural formula type of thing either side because the space there is just a little bit too small. Now that leaves the other products, and you can see that I've drawn the carboxylic acid, propanoic acid. How does that propanoic acid form? Well, again, just look at what's left. The acid anhydride here, and we'll highlight it in green. This part of the acid anhydride does not end up in the ester. This part of the alcohol does not end up in the ester. And actually you can see, if I highlight these slowly for you, that you've got the ingredients that you would need. So here we go, CH3, CH2, COO. That's this part here on the left, that's this part just here, isn't it? That part has ended up in the carboxylic acid. But I've also got another hydrogen, but bear in mind there's this hydrogen here from the alcohol. That hydrogen, of course, joins with that other part from the acid anhydride to form your carboxylic acid as the byproduct. So how will I get 3 marks? Well, you can see there's going to be a mark for the name. We'll talk about it in a moment. But have I drawn the correct ester? Yes, I've got a mark. Have I been able to predict the other product from the reaction? That would be my 2nd mark. And the ester here, of course, is ethyl propanoate. Why is it ethyl propanoate? Well, this group here at this end of the ester is the ethyl group. And as we saw on the previous page, the carboxylic acid portion, or the bit derived from a carboxylic acid or its derivative, 3 carbons there, so of course that would be propanoate. Now if you did this particular exam paper and saw this question, I suspect it would have filled you with a little dread. It's a difficult question to even begin to understand what you're expected to do, and we'll talk you through it. Because you're told that we're going to form biodiesel from 1 mole of a vegetable oil. Tell you what, let's unpack the question a little bit before we go any further. A vegetable oil is a triglyceride. So I've got 1 mole of a triglyceride. Now I'm reacting it with excess methanol. That's a little bit of a clue here, and we'll talk about that because this is going to be a trans-esterification reaction. So if you go back to carboxylic acids part 2, it's or maybe it's part 1, I've forgotten now. But if you go back to your notes, it must be part 1, then it would look at the trans-esterification right at the end of that pack. Now your vegetable oil, of course, reacts to form new esters. They would be the biodiesel. It's awkward here because you're given a lot of information. You're given a molecular formula, and that molecular formula, you're told, is going to be produced in double the quantity of the other product, which we're only going to form 1 mole of. So I've got to draw the structure of the vegetable oil, showing the ester links. I've got to draw my original triglyceride from those 2 molecular formulae. And actually I'm told that I don't have to draw it with a lot of detail. The hydrocarbon chains here I can show as CXHY. Well, how am I going to do this? It all hinges on me understanding what biodiesel is. Biodiesel is a methyl ester. So all biodiesel, when made from methanol, would have a generic structure that would look like that. It's got the ester group, but crucially, it's got a methyl group straight after the ester. Then I've got some sort of hydrocarbon chain. So let's bring that into these molecular formula. This one I've underlined in red then is C19H34O2. So if I try and draw out what that product might look like, I know it's a methyl ester. So now all I need to do is piece together the rest of that structure. Now the rest of that structure is going to have carbons and hydrogens. You can see here the 2 oxygens, so that's covered. You can see that I've got 2 carbons shown, starting with 19 in the question. So that means I must have 17 carbons in that hydrocarbon chain. I've got 34 oxygens in my molecular formula, hydrogens, but 3 of those hydrogens are in the methyl group. That would leave me with 31 of these hydrogens in the chain. So I'm beginning to understand what this CXHY might be. For this particular compound, I've got C17H31, and I've worked it out based on my knowledge of biodiesel being a methyl ester. I've drawn the bit of the structure I know, and I've used the remaining atoms to predict what that chain would be. Now, before we go any further, remember the question says we're going to get 2 moles of this, so 2 moles of that ester. So I'm just going to put that as a little note to myself. I've worked out what the ester is, and I'm going to just write times 2. I can do the same thing here with my other ester. And in fact, I'll give myself a bit more space. There it is, C19H36O2. So if I draw this out, this is going to be obviously a methyl ester. It's biodiesel. So of my 19 carbons, well, again, 2 of them I've already used, so there are 17 left in that hydrocarbon chain that's going to make up the R group. I've got a few more hydrogens in this case. In fact, I've got 2 more, so it'd be C17H33. Now remember, I've only got 1 of those because the question says I've got 1 mole of the ester, of that ester being formed. And actually now I can begin to build up my original triglyceride. I've done all this thinking. I haven't got any marks yet because my marks are coming from drawing the structure of the vegetable oil. So your vegetable oil should be based on glycerol. So if I start drawing the glycerol portion here in black, well, there we go. Propane 1,2,3-triol is the glycerol as its IUPAC name, and this is going to be the beginning of my triglyceride, my vegetable oil. In fact, I'm expected to recognise that my vegetable oil is going to have certain groups in. I'm expected to recognise it's an ester. Now I need to draw the remaining part of that ester, and this is when I go back to what I've drawn already. The bits of these molecules of biodiesel that have ended up in the ester can be worked out. Should know it from my carboxylic acids pack, but you can see here, let's highlight it, I'm using methanol to form biodiesel, and the methanol ends up as methyl groups in these products. That means that the rest of those esters, so the bit here in red, has effectively come from my triglycerides. The bit here in blue has effectively come from my triglycerides, so I need to incorporate those chains into my triglyceride. A triglyceride would have 3 ester groups, and of course I can then bring in the knowledge that I've got from the question. There are going to be 2 of this one that I've drawn in red, and only 1 of the one I've drawn in blue. Does it matter what order I put them? Actually it doesn't. It's a difficult enough question anyway, so I'm expected to incorporate these 2 parts from biodiesel. So C17H31. I'm going to draw both of these next to each other. It doesn't matter what order you put them in, but I know there are two of them, so there we go. Put them together. And finally, the other part of that structure, and this is the one with 33 hydrogens. So how do the marks work out? Because you might think that's taken quite a while just to get 2 marks, and to be honest, I would agree. If you've attempted this question and tried to draw a triglyceride, well, if you've shown this portion that I'm putting a black box around now, if you've got this far and that is all correct, so you've got a triglyceride with all of that, you're going to pick up a mark for that. So if you've drawn a structure that includes that part, you've got your first mark. To get your second mark, you need to have these 3 chains. Let's highlight them in blue. There we are. They need to be correct. You need to have 2 that are C17H31, 1 that's C17H33, and if you've done that, well, I think you've done a good job. It's a tricky question, that one, but hopefully that's given you some idea of what the examiners were hoping you might do in terms of answering that question. The next part then looks at a fatty acid, and it goes into a bit more detail about the idea of C19H34. It tells you it's a methyl ester of ZZ octadeca 9,12-dienoic acid, and it gives you part of the structure. Again, let's go through what the question actually wants you to do. It wants you to complete the skeletal formula for the next part of the hydrocarbon chain, but it only wants you to go up to carbon number 14. Do not make your life more difficult than you need. Read the question. Yes, there are 19 carbons, but you've only got to draw up to 14. Now, you're obviously given the structure to start off with. I've added my answer in here, so let's highlight what was already given to you in yellow. You were given this part in yellow, and of course you were given up to what was carbon number 8. So I need to unpack the name. You can see the structure, but I'll talk you through it. So I've got octadeca 9,12-diene. So I've got a carbon-carbon double bond starting from carbon number 9, and you can see that's what I've got there in my structure. And I've got a carbon-carbon double bond starting from carbon number 12. Actually, you can see as I've drawn this, I've numbered my carbon. So after carbon 8, I've drawn carbon 9, drawn my double bond to carbon 10, then I've gone down to carbon 11, carbon 12, now I know I need to put another double bond in, carbon 13 and carbon 14. The question only wants me to go to carbon 14, so now I can stop. But I'm told that I have to show the Z chemistry for those double bonds. Now, of course, Z chemistry would suggest that the groups on those double bonds are on the same side. And so when I look at carbons 8 and 11 there, well, they're on the same side as each other. So that was for the first double bond, the one between carbon 9 and 10. If I do a little dotted line there, you can see those 2 carbons, 8 and 11, that I've numbered, circled in yellow, are on the same side. Need to do the same thing for the double bond at carbon 12, so I've put carbon 14 on the same side as carbon 11, and therefore the same side as carbon 8 to show that Z stereochemistry. So what we've got then is 2 marks, and we've got 2 marks because we put the 2 double bonds in the correct positions, and if we've done that and shown them as Z isomers, we would have picked up our second mark. The final part of this particular page carries on with this ester, and it wants you to do a combustion equation. This is a bit more complicated than the combustion equation we saw at the beginning of the exam paper. The molecular formula is larger, but it doesn't necessarily put us off. 19 carbons, we're expecting to see 19 carbon dioxides. 34 hydrogens, we're expecting to see 17 waters. Now, when we do that and I reveal the answer, you can see that we've got 26.5 molecules of oxygen. Just look at your work in here for 26.5. Did you write it? If you did, well done. If you didn't and you got this question wrong, is it because you've written 27.5 oxygens? Because if you've written 27.5 oxygens, you've forgotten about the 2 oxygens that are here as part of the ester. Just highlighted them there for you in yellow. And this is a classic mistake. Examiners quite like asking combustion equations in the second year that involve oxygen and compounds that contain oxygen, because it makes the balancing just a little more difficult. You have to think about a bit more difficult than an AS alkane type question. By contrast, the final question on this section before we get into the multiple choices is about the greenhouse effect, and it says combustion of biodiesel produces carbon dioxide. Well, you've just included that in your previous equation. So we've got the infrared spectrum of carbon dioxide, and we're here asked to state how this infrared spectrum of carbon dioxide in figure 3 is not what you might predict from the data in the data booklet. Now, one of the things, it does hinge on your understanding of carbon dioxide, and there are a few people that fell into a little bit of a trap here, and the examiners have left it quite open. They've given you no structures. Of course, you've got a peak here that are around about 2,400. It doesn't correspond to the bonds that you're thinking. But do you know what bonds are in carbon dioxide? You should. Carbon dioxide, of course, and we'll reveal the structure here, contains COO bonds. Now, some papers I looked at, people had referred to as CO single bond, but that's not in carbon dioxide, so that isn't going to be credit worthy here. So CO2 contains C double bond O, so we would expect a peak for that bond to be in the region the data sheet says. There it is, 1680 to 1750 centimetres to the -1. And of course, when you're dealing with IR questions, it is good practice, in fact it is necessary, to show the bond that we're talking about. So identify the bond we'd expect, and according to the data sheet that should come around about 1700. I've given the precise range from the data sheet, but it doesn't. It comes around about 2400. That's why the spectrum is not what I might predict. So we've been through all of these questions now on this first section of this exam paper. There's a separate video to talk you through how the multiple choice questions are answered. Hopefully you find it useful. If you have any queries about anything you've looked here, have a word with your teacher. They would be happy to help.